All right, so 5.5 is a section in your text called substitution. Depending on what class you have or what instructor you have, substitution is most often referred to as U substitution, or more affectionately known as U sub, right? But all of those things describe this idea, this concept that we're going to be talking about today, okay? And so let's revisit what we know. We are getting close to the end of the chapter, and so therefore this list is growing. You can also think about this as a effective topic list, though the topic list for chapter 5 has already been posted, so you can take a look at that. But reviewing what we've covered, we've taken a look at approximating area with rectangles, finding exact area with geometry, and noting that we have to be really careful that they've told us that it's a triangle or a semicircle. We can't just assume that something that looks like a half circle is a half circle. We actually have to know that the equation matches that. We've talked a lot about definite versus indefinite integrals. This is certainly a place where if you feel like you want to become a little bit more fluid with the computations and the calculations, that spending some time practicing those definite and indefinite integrals will be a good investment of your time. We've talked about some theorems, which I know are not everyone's favorites. However, they are fairly relevant in this chapter. So we've looked at the average value theorem. We've looked at that fundamental theorem of calculus part 1, as well as the fundamental theorem of calculus part 2. And then on Wednesday of last week, we finished off with the net change theorem. So one more theorem to add to the bucket. But as I'm thinking about the work that I've seen from students in terms of quizzes, one area that I would really encourage you to spend a little bit more time clarifying for yourself before that exam on Friday is the fundamental theorem of calculus part 1, okay? That's where I'm seeing the most mistakes. And so that's an area that I think overall as a class, we have some room to grow in, okay? Additionally, I think that if we're also thinking about preparing for the exam, the definite versus indefinite integrals, folks are making some computational errors. So I'd really encourage you to double check your work, write out a little bit more than you need to, be really, really careful about those positive and negative signs, okay? All right. So what's new? Today, we're going to think about questions that we, up until this point, have been able to solve only if we can sort of sidestep the situation. And so in particular, looking at questions where we have maybe this is something that we all know how to do, right? Integral of x squared dx. And what does that give us if we integrate or find the antiderivative of x squared? X cubed plus 3. Excellent. And what else do we want to make sure we have here? Yeah, that plus c, right? And so that's something that we know how to do. But today, what we're going to be taking a look at is things that maybe look a little bit more dressed up, like what if we had sine x plus the square root of x squared dx. Okay, so now we're returning to the idea that sometimes we just have an x that we're doing something to, and sometimes we actually have a whole other function that we're dealing with inside of that other function, okay? And so today we're thinking about the chain rule, but for integrals. Okay. So if you think about how often we use chain rule when we did derivatives, like pretty much every problem, now we're going to be learning the equivalent for integrals. Okay. And so anytime you hear someone say U sub or U substitution, they're really trying to get you to think, how do we sort of undo that chain rule? Okay. So let's take a look at the concept, and then we're going to spend pretty much all of today just working through examples and examples and examples. Okay. So when we differentiate composite functions, all right, when we differentiate, and differentiate just means to take a derivative, all right, so differentiate right here, when we see that word, we means take derivatives. And so if we think about what it looked like when we had a function inside of another function, we would take a derivative of, let's say, f, and then inside of f wasn't just x, but it was like another function. And so thinking about that symbol notation, how would we write the derivative of f of g of x? Going to be a really long morning if you're just waiting for me to answer everything. Okay, I know this takes a long time to type too. All right, there we go. So we could have our derivative of the outside one, so f prime, but we keep the inside the same. And I think when we were doing our original notes, we sort of did this outer function in the pink, and then our inner function. When we took that derivative, we had to multiply by that derivative of the inside function. Okay. And so anytime we saw this, we needed to say, okay, I've got a function inside of another function. I have to accommodate for this somehow. And so if we think about anytime we have something that is not just x, then we do our f prime of that function, and then we have to take the derivative of whatever's not just x. Okay. Now, the reason why that's so important is because we're now saying we have something like this. How do we get back to what the function originally was? Okay. So for example, if we have a function where I have its derivative of the outer function times the derivative of the inner function, what was that original function? And so maybe let's start with a couple examples. What if we had something like this? The derivative of something is 2 sine x times cosine x. What function did I take a derivative of to get 2 sine x times cosine x? Okay, we have one idea for sine x squared. Okay, all right. So remember when we write our trig functions, when we're squaring them, we have sort of that squared in the middle, but I love the concept here, which is that the outside function is sort of the squared part. That's where we get 2 times sine x from, because we use the power rule. And then we have this sine part that we have to take the derivative of, which gives us the cosine piece. Okay. All right, let's try a couple more. Let's see. So the derivative of what is going to give you what function did I take a derivative of to get what I have on the left hand or on the right hand side? Perfect. All right. All right. So we can sort of see here, we've got our derivative of the outer function, which is looks like a power rule situation. And then the derivative of the inner function there. And so when we think about what function it came from, we're going to get x cubed plus natural log x minus 1 all to the 5th power. Okay. So that's effectively the game that we're playing today. All right, which is here's some function, but I want you to figure out where it came from. Okay, what did I take a derivative of to end up with the thing that I'm integrating? So with that, let's get started. All right, so we're going to do this in sort of 4 chunks. Okay, we're going to take a look at sort of what I think is a fundamental level, a level that I want us all to be very comfortable with. And in this level, what we're going to be focusing on for ourselves is decision making. So decision making. And identifying what we're going to call our U. Okay, that's going to be the focus of the first section. When we move on to level 2, you'll notice that I call this one some sneaky cases. And the reason why I call this sneaky cases is because these are very common U sub problems where people forget to use U sub. Okay. So very common situations where people forget to use U sub, which is why we're calling it the sneaky cases. But I want us to remember, all right, we're going to have to use U sub. Okay. And so we'll spend some time practicing the sneakier cases. They're not necessarily hard. In fact, sometimes they're so simple that we just forget to use them. Okay. Then we're going to take a look at some beefed up practice. So things that look a little bit more scary, lots of square roots and powers and fractions and all sorts of things. Yes. And so we're going to try and shore up our skills a little bit more there. And then we're going to finish today with the definite integrals. Okay. So how do we set up and solve when we have bounds? And so noticing that we have our 0 and our 1. And so how do we solve problems when we want to look at definite integrals? Okay. So that's sort of the flow of where we're going. I anticipate that we're going to get through level 1 and then we'll see where we are. Maybe it'll be a good time to take a break, but let's kind of see. Okay. So, all right, here we go. Example 1. So we've got sine x times cosine x. All right. So I'm going to walk through this problem without necessarily connecting it to the concept that we just saw before. Okay, so we're going to sort of approach this one very procedurally. As we're doing so, though, I think it would be important to ask questions as they come up on your end, like, why are we setting things up this way? Why can't we set it up a different way? And thinking about how decisions are made, okay? So when I see a problem like this, I see sine times cosine. And immediately I'm thinking that I'm going to need some sort of u substitution. Okay. And so in this case, I'm going to let u be sine x. Okay. So I'm going to choose this to be my u. Now, if I wanted to rewrite the question, then I could say the integral, and instead of writing sine x, what could I replace sine x with? I could replace sine x with u, right? Because right here, I've said u is the same as sine x, right? So everywhere I see a sine x, I'm going to put a u. And if I don't do anything else, then I have cosine x dx, right? I keep the rest of the question the same. However, as mathematicians, we should always be incredibly skeptical when someone starts mixing letters together. We've got a U, we've got an X. That just seems like it's not going to go very well. And so what we're going to do is we're going to actually take a look at our U and see what else we can do with this, in the idea that we want to get rid of all the things that have x's and instead write the entire equation in terms of u. Okay. All right. So let's go back to this u for a moment. I have u equals sine x, and du, if I took the derivative of u, that means I'd have to take the derivative of both sides. What's the derivative of the other side? Let's do this. Instead of du, I'm going to write du dx. Kind of like how we had dy dx equals, and good, we get cosine x. Okay. Now I'm going to ask you to do one last thing with this expression right here, which is let's get everything that has a u on one side, but everything that doesn't have a u on the other side. What do I need to move from the left-hand side? The dx, okay. Now it looks like du divided by dx. How do I move the dx? Multiply by dx, exactly. So du equals cosine x dx. Okay. Now, let's pause for a moment and say, oh shoot, cosine x dx. Everywhere I see that, what can I replace that with? What's another way of saying cosine x dx? Yeah, du. So everywhere I see a cosine x dx, I can rewrite it as du. So I get let's do it here, the integral of u du. And the du came from the cosine x dx, and the u came from the sine x. Okay. So everything that is blue matches all the way through. Everything that is yellow matches all the way through. It's just like a different way of saying that. Okay. What's the integral of u? Maybe another way to think about that is, what would be the integral if I told you, what's this? Yeah, you'd probably say this is x squared over 2 plus c. Well, what do we have here? U du is going to be exactly like Graham says. We're going to get u squared over 2 plus c. Okay. And Richard, that is the perfect summary. In fact, maybe I should just hand the class over to you, right? Does this work because we changed all our x's, all our x's to u's? Exactly. Once we've changed everything, all the x's became something in terms of u. Now we can treat it just like we treated a question that had all x's. Okay. So the integral of u du is literally just u squared over 2 plus c. Okay. Now, if we left our answer like this, unfortunately, that would not be completely correct. And the reason is we were asked about our question with x's. And so if we answer with u's, we haven't really addressed the question. So exactly. All right. So I'm just going to finish this example, then Richard's going to take over for the day. Okay. Now we change it back. Okay. So we want our answer to now have x's, but not u's. So what do? We say u squared is really sine squared x over 2 plus c. And that, my dears, is our answer. Okay. So I'll give you a moment to kind of look over that on the screen. Yes, so we just plug everything back in. And by everything, typically our answer will have u in it. And so whatever we said u was going to be equal to, we just have to put that back in. Okay. So if I ask a question with x's, then the answers should be with x's. If I asked a question with u, then your answer should be in u's. Okay. Now, are there questions about what we did here? Mm. All right, Eric and Richard are just going to tag team this lesson from here on out. All the awesome questions today. How did you know which one to make you? So this is the critical question. How do we know which one to make the U? Now, this example I picked on purpose because turns out you can have two possible answers for that. Okay. Most of the questions we will have will only really have one that will work out well. But this level 1 practice, I kind of want us to try different ones and see why some of them might be less effective than others in terms of choosing the U. Okay. So let's go back to the original problem now. I'm going to recopy it over here. The integral of sine x cosine x dx. Okay. Now, the first time I said, just go with me here. I'm going to let sine x equal to u. But this time I'm going to say, let's actually let cosine x equal u. So u equals cosine x. Okay. Now, if u equals cosine x, what does du over dx equal? Negative sine x. Good. Okay. Now, as mathematicians, again, we think, okay, it's always a little weird when the letters are sort of mixed together. And so we want to get rid of that dx on the left-hand side. So we're going to go ahead and multiply that to both sides, and we'll get du equals negative sine x dx. Okay. And so I've got cosine x. Everywhere I see a cosine x, I can go ahead and put u. Okay. But in my actual equation here, I have sine x dx that I haven't substituted yet. And then I have an expression that's kind of close to that, but it's not like a perfect slipper Cinderella kind of situation, right? It looks a little bit different. So my question to you is, how can I make this bottom expression perfectly match the rest of what I need it to match in the integral? Put a negative du. Oh, okay. So this negative sign, let's go ahead and move it to the other side, right? I don't want negative sine x. I want a positive sine x. So let me divide everything by -1. So divide by -1, and we get negative du equals sine x dx. Okay. Well, now that means that everywhere I see sine x dx, which happens to be split up, but that's okay. Sine x dx, everywhere I see sine x dx, I'm going to replace it with negative du. And so let's see what happens. I get the integral, all right? I'm going to replace the u, the cosine x becomes u, and then the yellow parts become negative du. So I've got the yellow part that matches with the other yellow parts on the left-hand side, and then this blue u is my blue cosine x. Well, this really says u times -1 times du. And so I'm going to pull that negative sign all the way out to the front. So I have negative integral of u du. Okay, so we're just using that constant multiple rule Or we can think about it like a vertical stretch that I'm just taking that part out so I can multiply it back in later. And if I integrate this, I'll get negative u squared over 2 plus c. Okay, well, at the end, I want to make sure that I put everything back in terms of x. So that gives us negative cosine squared x over 2 plus c. So we set this up two different ways. We chose one function as our u in the left-hand side. We chose sine x to be the u. And when we did it again, we actually chose differently. We let the cosine x be that. Now I argue that these two are the same answer. I will, however, let you on your own time figure out how these two are the same answer. Okay. The bigger point of this question, though, is that we could, in this question, as Eric said, have u be one of two options. It was the sine x in one case, or it was the cosine x in the other case. But as we move deeper into the other questions, we're going to find out that we don't always have as much choice. In fact, what we're practicing here is which u is going to help us move forward in solving the question versus which one is actually not going to make our lives easier. Okay. So let's take a look at this second example. Okay. So we've got the integral of sine x over cosine cubed x dx. And so let's set it up two different ways just to see. Okay. So what might be one option for our u? Let me give me an option for you. Okay, so u equals sine x. All right. Someone else give me another option for you. What else could I choose as my u? Maybe let's do it vertically. Okay, we've got u equals cosine cubed x. That seems to be another option. Okay. Any other options that folks want to try? One over cosine cubed. Okay. So we could say u equals 1 over cosine cubed x. All right. Okay. Now, keep in mind that whatever we choose for u, we also, as we did above, every u that we chose, we had to find du dx. So we let u equal sine x, we had to find the derivative. We let u equal cosine x, we had to find the derivative. Okay. So of the three that we pitched here as ideas, let's see which du dx's we can find. Okay. So let's see, if I take u as sine x, my du equals cosine x dx, right? Okay. Well, what if I choose the second option? What do I get for my du? Well, if this is our u though, like sine x, when I take the derivative, I get cosine x. I don't get cosine cubed when I take the derivative. Ah, no, you're fine, you're fine. I'm glad you clarified that. But for the second one, if we choose u equals cosine cubed x, what is the derivative of that? Ooh, maybe if we rewrite it like this, cosine x cubed, I got to use chain rule here, right? I got an inside function, I got an outside function. All right, so I got 3 cosine squared x times negative sine x dx. Okay. Okay. Uh, anyone care to find the du over here for the last option? Well, I think it would sort of be in line with what we've been doing, but maybe we could say that it's even more complicated. Okay. And so we've tried some options, and now let's kind of see what matches with what we have, and does it help or does it not help? Well, the hope, Natalia, is that we're going to be able to sort of do this thinking in our heads and think about ultimately which one is going to be the best option. Okay. So the whole point of this exercise right now is like, but how do we choose that u? Okay. So let's see what happens. If I wanted to put u equals sine x and du equals cosine x dx into this equation, what would it look like? Well, the sine x, I could put a u, right? Do we all buy that this sine x becomes a u in the numerator? Does that seem good to folks? Yes, okay. Now I gotta get rid of this cosine cubed x dx somehow. What are our ideas? What do you mean by not gonna happen? Dx is in the numerator. Which one did you mean, numerator or denominator? Ah, okay. Yeah, this cosine x is down at the bottom of the fraction, while the dx is actually in the numerator. So we'd almost have to split them, and we don't have an algebraic way of splitting them. Yeah, exactly. This cube piece, but there's no cube here. All right. So this one, whoa, so this one doesn't seem like it's getting us anywhere. Okay. What are our thoughts on this second option? Does that seem like it's going to help if we try and substitute things in? Or is it going to become more complicated? Yeah, this one is also going to get more complicated. And this one, well, even just taking the derivative to find the du was like a lot of work, okay? Now, I don't want us to look at this question and be like, wow, it's not even solvable, okay? This is actually a really good chance for us to think about how we choose wisely. Okay, so we sub u for dx. What do you mean by that? Okay. So let me rewrite the question again, just so we have a clean example to write with. So sine x over, and I'm going to go ahead and write this as cosine x cubed dx. Okay. Now, here is a little hint in terms of choosing your u. Okay. There are no hard and fast rules, but there are some things that are useful to try. And one of those is that if you have something raised to a power, if you have something raised to a power, that can be a good choice for your u. However, this is not like a Goldilocks and the Three Bears in the sense that, you know, when Goldilocks was like eating the porridge, like one was too hot, one was too cold, the other was just right. You sort of done something similar to that in choosing the u's that you did earlier. So some of us chose this, which was maybe we could say is too cold. Some of us took a bunch more for the u and we would maybe say that's too hot. But if we're looking for sort of that sweet spot, what we're looking for is if you see something to a power, the thing that is raised to the power is oftentimes, not always, but oftentimes a good choice for the u. And so if we try u as cosine x, what does that give us for our du? All right, if you choose u as your cosine x, really close, give me two more letters with that. Negative sine x dx, there you go. Negative sine x dx, okay? And this means everywhere I see a sine x dx, maybe I divide that negative 1 over. And everywhere I see sine x dx, which is, sine x dx, I'm going to replace it with negative u. Okay? So before we solve the problem, loved the idea of picking sine x because we know what the derivative is. Unfortunately, as Ethan pointed out, that derivative didn't quite match because it was raised to a power in the actual problem. I also loved the idea that if it's not sine x, maybe it's the other function. But what happened here is just we took too much of the function. We didn't want the cosine cubed. Turns out we just wanted the cosine piece. Okay. So sometimes when you're choosing your u, less is more. Okay. So let's make our substitutions now. We're going to end up with the integral of 1 over u cubed times negative du, okay, which is going to give me negative. And how could we write the 1 over u cubed so that we would be able to find the integral? U to the negative 3. I love it. I love it. Okay, so let's rewrite that as u to the negative 3. Are we allowed to use the power rule here now? Or is this an exception to the power rule? Yes, yes, we can. Good. Okay, so we've got negative, and I get u to the negative 3 plus 1 over negative 3 plus 1, and then a plus c at the end, which gives me negative. Let's make sure we add properly here. U to the negative 2 over negative 2 plus c. All right, what is the sign of our final answer? Positive or negative? We're going to end up with positive or negative? Yeah, positive, because we've got a negative and a negative. Just going to make it positive. And then what is another way to write u to the negative 2? Good. So I have positive 1 over 2 u squared plus c. Okay. We understand why there's a 2 in the denominator. Yes. Okay, so the 2 was from that negative 2 that was down there, right? But then what Thea said for the another way of writing u to the negative 2 is to bump that u squared down to the bottom. Okay, good. Now the question was asked with x's, so we need to answer it in terms of x's, which means that our final answer will look something like this: 1 over 2 cosine squared x plus c. And there we have it. So let's kind of take a look at our thought process, okay? I think very, very valuable exercise over here, which is to figure out what your u is. That's a great place to have conversations with each other as you study. How do you know which one is the u? Well, let's try this one. Let's see. Oh, nope, that wasn't helpful. Okay, let's back up. Let's try something else. Okay. Again, this is a great example of not always, but oftentimes whatever function is raised to the power is a good choice for the u. Okay, because what happens is you end up only bringing it to a question that you can solve with power rule. Okay, at the end, you just have to make sure to put your u back in. All right, let's try one more here. So we've got the integral of 2x plus 1 times the square root of x squared plus x minus 3. Give me some choices for you. What might be a good choice? What could be a potential choice? Let's not even label them good or not good yet. What could be one choice for you? And what could be another choice for you? All right, 2x plus 1. All right, that's one guess for you. What could be another choice? X squared plus x minus 3. Okay. Now, just because this is only the third question we've done, let's say someone was like, well, why couldn't it be the square root of x squared plus x minus 3? Valid thought, okay? So we kind of have three options like we did before. So let's go ahead and find our du's and see which one of those might be most helpful. All right. So when we take du of the first one, what do we get? All right, when we take the du of David's suggestion for u, what do we get? Two dx, love it, 2 dx, okay? Let's do a quick peek back at the problem. If we choose u as 2x plus 1, and then we get 2 dx as our du, does that help us in this question? Does it seem like it's going to be helpful? Yeah, I would say maybe not, okay? So it doesn't seem to be getting rid of enough stuff for us, right? In particular, we still have this whole square root thing that we didn't even do anything with yet, right? So let's try the second one. All right, so we get u equals x squared plus x minus 3. Du is 2x plus, oh my goodness, 2x plus 1 times dx. Wow, that seems like maybe it would get rid of some stuff for us, okay? But to practice our derivatives, right, we have u equals the square root of that. If we were maybe thinking about Goldilocks eating that porridge that's too hot, or sleeping in the bed that is too firm, if I want to take du, I'm going to get 1 over 2 square root of x squared plus x minus 3 times 2x plus 1 times dx. I can find the derivative, but if I look back at the problem, I don't know that that's going to be helpful. So let's give this one a try, okay? If we use this, then when we go back to our original problem, everywhere we see 2x and dx, we can replace that with du. In other words, 2x and dx becomes du. And I'm going to be really careful about what I'm highlighting here. Everywhere I see x cubed plus x minus 3, I can replace that with a u. However, if I zoom in real careful here, I want to be very, very thoughtful not to underline, not to highlight the square root part, but just the part underneath the square root. Okay. So when we make our substitutions, we're going to have the integral of the square root of u, and then all the yellow parts I can replace just by writing du. And so I've turned this question that looked incredibly complicated into one that is just the square root of u du. And that, even if we don't like square roots, we know we can write it as u to the 1/2 du. Can we use power rule here? Or is this an exception? We can use power rule. Okay, now this is a place where, again, I'm still seeing some mistakes. And so I really want to encourage us to take the time to write it out. U to the power plus 1, okay, over the power plus 1. Don't forget that plus c. This is going to give us u to the 3/2 over, what does the denominator become here? What does that denominator become? Yeah, divide by 3/2. Okay, well, fractions and a fraction seem kind of gross. So if I'm dividing by 3/2, what is another way of saying that mathematically? Divide by a fraction is the same as multiplying by the reciprocal. Good, good. So we get 2/3 u to the 3/2 plus c. All right. Now let's go ahead. If we left our answer here, we would be so close. But if the question gets asked with x's, we need to have our final answer in terms of x's. And so what we'll end up with is 2/3 x squared plus x minus 3 to the 3/2 plus c. Okay. So let's get that whole question on one page. I think by looking at this, right, and in particular, these three options, it's okay to not be sure which one the u is. But a great thought process is to try a bunch of them out and see why they work, see why they don't work, okay? I think the more that you practice that decision-making piece, the easier it becomes to answer Eric's question of how do you know which one is going to be your u, okay? So when picking u, we could say to pick the one that looks least processed. Okay, because things like constants and radicals tend to disappear when we take derivatives, which means that the derivative of the inside is of the less processed component is more likely to end up being the piece we are looking for. Yeah, actually, that's a really good way of saying that. So let me scroll back up for a moment to the exercises I was asking you to think about earlier. Like, just look at this. Tell me where it came from, right? If we were to choose our u's going backwards, this might be the least processed one, right? That would be a great choice for the u, because when you undo the power rule, you'll end up with that fifth power. Okay, so I think that's a really good way of thinking about that. Additionally, we've said things that are raised to the power is a good choice for a u. Another good choice for u is if you see a function and, holy cow, you see the derivative of that function, this better be your u. If you see a function that also has its derivative in the problem, that's a good choice for your u. Okay. So I'll give you some time to marinate on that. We're going to take a break right now. When we come back, we're going to blow through quite a few more practice problems just to make sure that we're getting the hang of this decision making. Okay. And that's what we're really going to focus on for that next part of class. So let me go ahead and, all right. So let's take a look. Let's jump right in. So level 2 practice, some sneaky cases. And again, I really want to highlight these because these are very common u-sub scenarios where people forget to use u-sub. And I don't want you to be one of those people. I want you to be like, this is a sneaky case. I 100% know that we need to use u-sub. Okay. So let's take a look at example 4. So we've got cosine of 4x, and we're looking to find that integral. Okay. What might be some options for a u? What do we think? Let's try like 2 different options. U could equal this, or u could equal that. What do we think? Okay, so one guess is a cosine of x, and the other one is maybe just the 4x. Okay, well, if I choose cosine, my derivative will involve a sine. And I think right off the bat, I look back at the problem and I was like, there's no sine in there. So that just seems like it's not going to be helpful. Okay. But let's see what happens if we find du of the second one. So if we have u equals 4x, then du equals 4 dx. Well, let's see. If I let 4x be my u, that means that this part is going to become u. Okay. I just have a dx here, but down here, I have 4 dx. How do I get rid of that? I divide that 4 away. And so everywhere I see dx, I can actually replace it with du over 4. So dx will get replaced by du over 4, or we can think about that as 1/4 dx. Now you might be saying, what about that cosine piece? Well, let's see what happens when we put this all back in. The integral of cosine u times du over 4. Okay. If I wanted to think about my constant multiple rule, I could go ahead and pull out the 1/4 all the way to the front. 1/4 integral of cosine u du. Okay. Now, even though we have this piece is with the u, and this is a u, we still have the cosine left. But when we look at the actual problem, I think we all know what the integral of cosine is, right? So it didn't boil down to a power rule situation, but we do know how to find the integral of cosine. In particular, when we integrate, we'll get sine u, and then don't forget that plus c, right? And then our final step is everywhere we see the u, we need to replace it with something in terms of x. And so we'll get 1/4 sine of 4x plus c. So 1/4 sine of 4x plus c. All right. So give me a quick thumbs up if that seems like something that is making sense based off of what we talked about before break. Okay, so I've got a couple yeses here. I've got a few thumbs up. Okay, now again, I think I fully own that this part, like how do you know which one is your u, is perhaps the most important question you could ask yourself as you're practicing these, okay? All right, let's try example 5. What might be one option for a u for example 5? Five x plus 4, okay. 5x plus, I don't know why I said 4. That's clearly a 7. I'm so sorry. Okay. And if we found our du here, what would we get? we get, oh, so close. There's 2 letters I need. There we go. Thank you, David. I'm gonna let you take over. Richard, get it together. 5dx. All right. So the dx here is so important because remember, we're trying to get rid of stuff here, right? So we have to really be able to match every single piece and swap it out with something equivalent, okay? Now, in looking at what we are trying to match it to, is there anything I need to do to this du expression? I have du equals 5dx. Yeah, let's divide that 5 over. So we get du over 5 equals dx. All right. So everywhere I see 5x plus 7, which is right underneath that square root, I'm going to replace it with a u. And everywhere I see the dx, I'm going to replace it with du over 5. Okay. So I've got the integral of the square root of u times du over 5. Mission accomplished because I've expressed everything now in terms of u, right? There's no more dx, there's no more x's, everything is u's and du's. All right, what would be a good next step in terms of what to write here? And I know this is tricky because you all are typing in a chat versus bringing that 1/5 over. Okay, so bringing that 1/5 to the front, I agree. And what else might be beneficial as we're starting to write? Yeah, let's change that u to the 1/2 power, okay? So let's do both those pieces in the same step. I'm gonna bring that 1/5 out to the front. I'm gonna keep my integral u to the 1/2 du, okay? And now it's just power rule, so 1/2 or 1/5, sorry, u to the 1/2 plus 1 over 1/2 plus 1 plus c. And we get 1/5 u to the 3/2 over 3/2 plus c. All right. I'm going to keep the 1/5 here, but what can I multiply that by to sort of start to simplify this expression here? What can I multiply that 1/5 by? I can multiply it by 2/3. There you go. We're going to move that denominator up here, and then we've got u to the 3/2 plus c. And let's see, we get 2 over 15. And then what was our u? We said it was 5x plus 7. So 2 over 15 times 5x plus 7 to the 3/2 plus c. There we go. That's it. Okay. All right, let's take a look at these last two in the sneaky cases here. I'll give you a moment to take a look at 6 and 7. And when you think you have an idea for what the u should be in both of those cases, go ahead and send me a message with your guess about what your u should be in 6 and in 7. If you get a yes in a response, that means that you can go ahead and start working through that problem. All right, so I've got some good guesses here. For u for number 6, it is our 3x. And for number 7, it should be the x squared. Okay. So let's kind of talk through why these make sense here. So for number 6, u equals 3x, that means du equals 3 dx. And let's see, u is everywhere there's a 3x. I'm going to have a 3x. I'm going to have a u in the exponent. And then I might use this clever trick that we've been doing where I'm going to take the du expression, I'm going to divide by 3. Du over 3 equals dx. And brown color. That means everywhere I see a dx, I can put du over 3. Whereas everywhere I see the 3x, I can put a u. So I'll have a u in that exponent. Now that is going to get me to the integral of e to the u times du over 3, which is 1/3 the integral of e to the u du. And even though we have not technically done this section yet, when we think about what we know about derivatives, the derivative of e to the x is just e to the x, which means the integral of e to the x is e to the x. So we'll get 1/3 e to the 3x. Let me be consistent here, e to the u plus c. And then we're going to plug back in that 3x, so we get 1/3 e to the 3x plus c. Okay. So I believe that most of us had guessed that u would be 3x. Okay. And I know this is different because in the past I've said, well, the thing that is raised to the power is often our u. Okay. But we might think that one exception for this is when we have our exponential functions, that the thing in the power, when we have exponential functions, is also a good choice for the u. Okay. Now this idea here, though, that we've been using where we take that derivative and then we divide by that constant, that comes up quite a bit. Okay, so that's a good skill to have in your back pocket. All right. Are there any questions about example 6? How are we feeling on example 6? Well, example 7, I did have a few folks who guessed that it was going to be the 4x, okay? Now, if we chose it to be 4x, though, we'd still be left with this x squared piece, and we wouldn't know what to do with that, okay? And so by choosing the thing that is sort of inside of another function, that's another good way to think about a u, okay? So u equals x squared, that means du equals 2x dx. So everywhere I see the x squared, I can put a u. So this is going to go to a u. But let's see what I want to match in my equation. I still have this dx and the 4x. But when I took my derivative, I only had 2x dx. How do I make those match? Yeah. Well, like above, where all I did was divide that 3 over, I could also multiply both sides by the same number. So if I multiply both sides by 2, I'm going to get 2 du equals 2x times 2 gives us 4x dx. And now 4x dx is this dx and that 4x. And everywhere I see that, I can put a 2 du. Yes, Richard, that is absolutely fine. That's another way of looking at it. Okay, so let's see, when we substitute everything in, we should get the integral of sine u times 2 du. All right, because this is our 4x dx, but under a different name. And this u was our x squared. All right, let's pull that constant out to the front. To the integral of sine u, that looks like an n, sine of u du. Oh, I mean, we might get a wrong sign here, like a positive or negative, but we pretty much know how to do this problem. All right, so when we have the integral of sine, what do we get? No. Yes. Okay, so we get negative cosine. So we have negative 2. Well, let's do it. 2 times negative cosine of u plus c. And I'm going to replace the u with x squared, but I'm also going to bring that negative sign out to the front. I know, right? I totally see through that plan. Negative 2 cosine of x squared plus c. Okay. All right. So if we sort of zoom in a little bit, these examples, not too bad. Okay. Not too bad in the sense that they're good practices for the different ways that we choose u. And when we think about matching the dx part in the equation, our sort of skill has been either divide that coefficient away, like divide by 4, divide by 5, divide by 3. But in that same vein of thought, we can also multiply that du to make the coefficients match if we want to. Okay. So overall, how do we feel about level 2? You can send me a 1 if it feels like, yes, I get this, a 0 if you're like, I don't really know yet, and a -1 if you're like, is it the end of the semester yet? How are we doing? Okay. All right. So if you are feeling like towards like the 0, -1 end of things, and it might be beneficial on Wednesday to kind of come back to class and so we can do more examples and kind of think through this process a little bit more about like, how do we know what our U is? Okay. There's also some U sub built into the 5.6 and 5.7 videos. So sometimes just watching it in a different context will also make things a little bit more clear. But this is definitely a really common problem solving technique that we use when we're integrating. Okay. All right, let's try some more practice. Let's see. Ooh, level 3. Okay, so let's take a look at example 8. Now, I really did like when people were sending me like, okay, this is what I think the U is. So let me give you a moment to kind of put in your guesses, submit your guesses for what might be a good U for example 8. All right, what might be a good U? All right, I've got a few guesses in, and all those guesses so far look good. So if you've submitted a guess, you are correct. Yes, yes. Good, good, good. All right, awesome, awesome. Okay, so most common guess, which is absolutely correct, is that we are going to take the thing in the denominator, but not the power, just the thing in the parentheses. X cubed minus 3x plus 1. Okay, now, if that was your guess, what do you think the du is? Right, what do we get for our du? If this is our u, what do we get for du? Ooh, I see some guesses that are almost correct because there are these two letters that we absolutely have to have, right? Okay, so let's make sure that we have those two letters at the end, but only two of them, not like four of them. Just kidding. Okay, your derivative is almost correct there. We want to make sure we have a 3x squared minus 3 dx. Okay, so we take that derivative and we get 3x squared minus 3 dx. Now, now how though can I match this? Because I don't see 3x squared minus 3 anywhere in the problem. So how is that even going to be helpful? Ah, okay. So what if we do this? Du equals 3 parentheses x squared minus 1 dx. Well, this is actually much closer. I want x squared dx because I have x squared, or sorry, x squared minus 1 dx because I have that here. Just a little bit more dressed up than the previous examples we saw. We want to go ahead and divide by that 3. So du over 3 is what we will use to replace x squared minus 1 dx. Okay, so du over 3 will replace all of this in our equation. So we get the integral of 1 over u times du over 3. Yes? No? Ah, okay. I have some folks that are messaging me and saying, but what happened to the power? Yeah, we got to be so careful about what we're writing here. Yeah, that power sure better show up in my integral because I didn't substitute out the power, right? And so this is a really good example of like sometimes we're so caught up in our substitution that we actually forget the greater structure of the problem, which is that there is still that sixth power. Okay, so really good catch there with that sixth power. We do want to make sure that we keep writing that. Okay. Now, if we are to start to think about a form that would be easier to take an integral of, we might bump the 1/3 out to the front. And we might also write this as u to the -6 du. Okay. And then we'll get 1/3 u to the -6 plus 1 over -6 plus 1 plus c. All right, let's clean this up a little bit. We've got 1/3 u to the -5 over -5 plus c. And this should give us -1 over 15 u to the 5th plus c. And then we got to make sure we have everywhere we see our u, we're going to go ahead and put back in our x cubed minus 3x plus 1. So -1 over 15 x cubed minus 3x plus 1. Don't forget that power on this end too, to the 5th power plus c. All right. So, I mean, I call it a level 3 because we did need to be more cautious here about seeing that common factor and then being able to divide that over, right? It was just like an extra step where we had to factor out that greatest common factor so that we could then match it with the actual problem, okay? All right. Questions on number 8? All right, let's move on to question 9. All right. Same idea. Send me a guess for what you think the u is for number 9. Got a couple guesses so far. They are all correct. Every single guess so far is correct. This is awesome. So awesome. All right. So x minus 1, definitely going to be our u. Right. So everywhere I see an x minus 1, I can replace that with a u. All right. du equals all right, what do we get when we take our du here? Well, this is actually the nice thing about like sending me a direct message is nobody else has to know if your answer was incorrect. Yes, 1 dx, there it is. So du actually just equals our dx. That actually makes our life so much easier. Everywhere we see that dx, well, we just replace it with the du. We don't even need to divide by anything, okay? All right, let's substitute in. We get the integral of x over the square root of u du. Yep, go back to that skeptical piece, right? We have x's and u's together. We cannot have x's and u's together, okay? We cannot. So we still have to figure out how to get rid of that x. Another way to say x, what if I add 1 to both sides? Everywhere I see an X, and let's do this in maybe like a nice light blue color, this X, we can replace with U plus 1. Okay. So that's what makes this one sort of a little bit more complicated than the previous questions, because you're subbing out some of the things in a traditional fashion, and you still have to do a little bit of algebra to kind of get rid of that other X. Okay. So let's see what we get. The integral of U plus 1 over U to the 1/2 du. Okay. So with that extra step, now we've been able to replace all of the X's with some variation of U. Okay. Now, what I really like about this problem is that it highlights a very common misconception that I've seen in some of the quizzes. Okay. Now, typically, what a lot of folks are doing is they're saying, I got one term on the denominator, so I'm going to move it up to the numerator with a negative power. And it begins like this. U plus 1 times U to the negative 1/2 du. Okay, people are just saying, well, I know this is a negative exponent, so I'm going to write it here as a negative exponent. And then people are doing this. And then they go on their merry way. Why is this so bad? We got so excited about using one of our strategies from algebra, which is like move that exponent up to the front, that we forgot about one that's even more basic than that, which is this is like U plus 1, like in parentheses, which means this is also U plus 1 in parentheses. Yeah. I mean, sometimes the divorce is better for the child involved, but you know, those are personal decisions. I won't presume judgment on folks. But the parentheses here are so important, because what I'm seeing on a lot of those mistakes is people are not then distributing this correctly, and then their whole answer is wrong. Okay. So a really good place to kind of pause, make sure you have parentheses where appropriate. And if you now distribute, you should get U to the 1/2 plus U to the negative 1/2 du. Okay. Another common place where I'm seeing mistakes is when folks are combining the exponents. There are very strange rules happening there. So exponent properties, definitely look over those, make sure you're using the right rules. Otherwise, your whole answer is going to be wrong. Okay. All right. Fractions, negative fractions, and the power rule. I wanted to do this because I know this is where we are struggling. So U to the 1/2 plus 1 over 1/2 plus 1. We've seen this one a bunch so far today, but I see a lot of folks who do this part correctly and then they don't do the next part correctly. So we have U to the negative 1/2 plus 1 over negative 1/2 plus 1 plus C. Now, in particular, some of the folks who are not getting this correct are not even bothering to write this out. If you cannot be bothered to write it out, I don't know what to tell you. Okay. If you can't write it, take the time to write it out and you get it wrong, I don't really feel bad for you. Okay. So take the time to write it out. If you know that is a place that you tend to make mistakes, take the extra 15 seconds and write it out. Okay. We get u to the 3/2 over 3/2 plus, what do we get over here for the second one? U to the 1/2 over 1/2. Good. U to the 1/2 over 1/2 plus C. All right. We can use our trick of multiplying by the reciprocal, right? So we get 2/3 U to the 3/2 plus, what's our reciprocal here now for the second fraction? 2. Good, because the reciprocal of 1/2 is 2. 2u to the 1/2 plus c. Okay. And same thing, like if this makes sense when you write it out, but then you don't write it out and you get it wrong, I don't feel bad for you. Okay. Take the time to write these out. Show yourself that work, convince yourself that you know how to do this. Because I know you do, but it's just trying to like do too many steps in your head. Okay. All right. Last thing, we got to put back in everywhere we see a u, we got to replace it with x minus 1. So that will give us 2/3 x minus 1 to the 3/2 plus 2 x minus 1 to the 1/2 plus c. And there we have it. As promised, a much beefier question than we saw in level 1 and level 2. Okay. If you are looking for practice problems, Paul's online notes has like a bazillion of these, and he'll show you the steps and talk you through, or not talk you through, but he'll write out the process. Okay. Definitely a good skill to invest in if you plan on taking a bunch more math classes. All right. All right. Down to our final few examples. All right. So this whole time we've been practicing this idea around indefinite integrals, but now we're going to put back in this idea of definite integrals. Like, how do we plug in our bounds? Okay. Now I'm going to show you two different ways because most instructors do it one of two ways. Pick one way, that's fine. Pick one way, you do that one way, but it's important to understand the second way, because a lot of times when you're like, you know, doing practice problems online or whatever, and you're trying to match the answer, if you do it, like some answer keys might do it one way and others might do it another way. So as long as you understand the two connection between the two, you'll be fine. But if you only know one way, it might make it harder to understand why some other answer keys are the way they are. Okay. So we're going to start off the same way that we have, which is we are going to choose a U, and we're going to also find a D. Okay. I think with WebAssign, a lot of times they are asking you for the numerical answer. So the way that you get there might be different, but as long as you get the same numerical answer, then you would be okay. Yeah. I think when I'm talking about like answer keys in particular, I'm referring more to like if a future professor is like, oh, here's my answer key for this homework, they might do it in a different way. And I just want you to be aware of that. Okay. All right. What are our guesses for the U here? What might we want to choose? All right. I see a few guesses so far. Richard, you're not correct. I'm just kidding. You are. All right. Good guesses coming in. I love it. I love it. They are correct. It's just because we appreciate you so much, Richard. That's why. Okay. Good guesses. Good guesses. Most of our guesses, actually all of our guesses, are in noting that when we are looking at an exponential function, that it is often clever and appropriate to choose the power as our u. Okay. All right, so let's take our du, then we're going to get 8x dx. All right, can we keep that, or do we need to modify this expression before we start matching things into the equation? Divide by 8, exactly, because when I look at the question, I notice that I see an x and a dx, but I do not see an 8x dx. So du over 8 will give me the x dx that I am looking for. Okay. So if we substitute this in, let's see what we get. E to the u times du over 8. Okay. If you write the following, it will be incorrect. Okay. If you write this, that is incorrect. What's wrong with it? What is wrong with what I wrote? Ah, very nice. Everything here in our original question, everything was with x's. But I sure did change these to u's. So here's where sort of the two methods kind of split, okay? Some folks like to change the bounds so that they are in terms of u. Okay. So they might say this: u of 0, right? Because the bottom bound is 0. So if x is 0, what is the u value that goes with it? Well, 4, 0 squared plus 3 gives me 3. So when I'm in x's, the bottom number is a 0. But when I have everything in u's, my bottom number should be a 3. right? Because if you're going to change some parts of it, you got to change all of it. How would I find the new number at the top? Find u of 1. Yeah. Let's take u and plug in 1. We get 4 times 1 squared plus 3, which gives us 7. That means that in my x bound is 1, but with u, it will be 7. Okay. Yes, that is precisely it. The other method is we sort of ignore it until we change back to x's. Okay. I don't do that method because I often ignore it and then forget to change it back. So then I get the wrong answer. Okay. All of my answer keys will be using this format. Okay. So just to be very explicit about that, all of my answer keys will use this method where I change the bounds. Once I change the bounds, it means at the end, because I'm finding a number, I don't need to plug the x's back in because I already changed it to a whole different problem, an easier problem. Okay. So let's see where this takes us. If I have this, I can go ahead and pull the 1/8 out to the front. The integral from 3 to 7 of e to the u du. All right, 1/8 e to the u, and I'm going to draw that vertical line. I'm plugging in 7 and plugging in 3. And I don't need a plus c because I have numbers. So like I'm finding an actual area. 1/8 e to the 7th minus e to the 3rd. Please don't turn those into decimals. All right. We're just going to leave it like that. And we can say at the end, we have e to the 7th minus e to the 3rd over 8 as our answer. Okay. So what I've modeled here is how the answer keys will be for this class in terms of changing the whole equation into u's, including the bounds. Okay, so this part down here, changing the bounds so that I get bounds that are with u instead, that's how all the answer keys will be. Okay. There is sort of another sort of school of thought, which is just leave them as x's and then we'll kind of come back and figure it out later. Okay, so let me redo the problem in a way that I think other folks might do it. So let's rewrite this over here. We have our integral from 0 to 1 of x e to the 4x squared plus 3 dx. And so with the same u, we get 4x squared plus 3 du equals 8x dx. So du over 8 equals x dx. Right, so that's all the same as the previous question. And so what other folks tend to do is they'll do this. They'll say the integral of x equals 0 and x equals 1 of e to the u times du over 8. Okay. So in particular, they are very clearly saying that this is x equals 0 and x equals 1, not u equals 0, u equals 1. Okay, that small change makes all the difference. Then they take their integral, they get 1/8 e to the u, plug in x equals 1, x equals 0. But in order to plug in their bounds, they have to put in, instead of a u, they have to put in 4x squared plus 3. So 1/8 e to the 4x squared plus 3, and now I could just write a 0 and a 1. And then we get 1/8 e to the 4 times 1 squared plus 3 minus 1/8 e to the 4 times 0 squared plus 3, which gives us eventually e to the 7th minus e to the 3rd over 8, which is the same answer that we got by switching the bounds. Okay. Either way is, they're both equally accepted in the mathematics world. Okay. Yeah. So for me personally, again, this is a very personal choice. If I'm going to change it to u, I might as well do everything and then not have to worry about it at the back end. That's my sort of logic. Okay. Some people, though, prefer to say, I'm going to do it exactly how I did everything else. I'm just going to, at the end, make sure I get it back in terms of x and then plug in the x numbers. Okay. If you are going to choose this method, though, you better write x equals in the bounds. Otherwise, I'm assuming those bounds are in the same variable as your actual problem. Okay. So if you're going to write it the second way, please make sure you write x equals the bottom number, x equals the top number. Okay. So let's see, we've got about 10 minutes left. We have 2 problems left. I think we can do it. All right. We haven't seen one of these yet. Secant squared theta times tangent theta. What are our guesses? They do look fancy. I like that word. Fancy sounds nicer than scary. Right? But let's think about this for a moment. What do we see a function and do we see its derivative? Like that's really what it boils down to. Do we see a function and do we see its derivative? Okay, I see some good guesses here. Some people are saying that secant theta should be our u, because my guess is folks who are saying that it's because there's a power here, right? So if u equals secant theta, what is our du? Like, what's the derivative of secant? Yeah, what is that derivative of secant? Secant theta, tangent theta, d theta. Okay, so if I rewrote this as the integral from 0 to pi over 4 of secant theta, tangent theta, d theta, I mean, that works. We've got everywhere we see this, we can put a du. That takes care of like this whole other blob right here. And everywhere we see this, we can call it a u. That totally works. Okay. Now, to Umar's point, though, it is possible to set it up a different way. It is possible to say, I want my u to be tangent theta. What's the du in this case? If u is tangent theta, what's my du? Secant squared. Secant squared theta d theta. And this, if I brought it back to the original problem, I could still accommodate for everything. Tangent would be this piece right here. And this secant squared theta d theta, this whole thing would be my du. Okay. So example 11, we could actually set up in one of two ways. And in this case, I would say they both work, kind of like the very first example that we did. Okay. Which one would we prefer to use? Would we want to do the first one or would we want to do the second one? I think there's benefits to both. Okay. So if you choose the second one, or sorry, the first one, I think it's important to consider, do you know your secant values? Like, because you got to find secant of 0, you got to find secant of pi over 4, right? And that's fine because secant is just 1 over cosine. So if you know your cosine values, that's absolutely fine. Alternatively, if you choose the bottom one, then you want to know, do I know tangent of 0 and tangent of pi over 4? So sometimes the bounds actually help you decide which one might be easier, okay? But let's go ahead and do the first one here, just because we wanted to. I am going to go ahead and change my bounds though. So u of 0 is secant of 0, and u of pi over 4 is secant of pi over 4. So I think, let's see, secant of 0 is 1 over cosine 0, which is 1 over 1, which is 1. And this is going to be 1 over cosine of pi over 4, which is root 2 over 2. So this will be 2 over root 2. If you feel like you know your tangent values better, choose the second one. Okay. But if we substitute this all out, we will end up with the integral from 1 to 2 over root 2 of u du. And that got simple real fast. I mean, the bounds are kind of gross, but the actual integral of u du is very straightforward for us. U squared over 2, I'm going to plug in those bounds. And we get, let's see, 2 over root 2 squared over 2 minus 1 squared over 2. What does that give us? 4 over 2 over 2 minus 1/2. So we get 1/2 as our answer. Right? So sometimes, again, you can choose one of two methods. It really depends on where you feel like you're more confident. I know for me, I just don't know my secant values as well as I know my tangents. So I probably would have chosen the second way. But again, it really depends on where you see those strengths. Okay. All right. Can we do that one last question in 3.5 minutes? I think so. Whoop. All right. What do we want our u to be here? It's the fact that some integrals work with multiple options. Yes, Ethan. So if you think about like sine and cosine are often paired together, if they're not raised to powers, then either one could be fine. Yeah. All right. What do we think about our u here? What's in the cosine? Yeah, pi x cubed over 2. All right, what's that going to give us for our du? We'll get 3 pi x squared over 2 dx, and all I want is an x squared dx. So I'm just going to move everything else to the other side. So 2 over 3 pi du is going to replace x squared dx. So x squared dx becomes 2 over 3 pi du. All right, let's change our bounds. U of 0 is pi times 0 cubed over 2, which is 0. And u of 1 is pi times 1 cubed over 2, which is pi over 2. Okay, let's sub everything in. We've got an integral from 0 to pi over 2. Now, these are my u bounds. They are not my x bounds. And then I have cosine of u, and then times 2 over 3 pi du. And as gross as that looks, 2 over 3 pi is a constant. Let's bring that out to the front. And then all we have left is the integral of cosine u du. We ask ourselves, what function did we take a derivative of to end up with sine or with cosine? And it is not negative sine, but it is positive sine. Plug in our bounds. Sine of pi over 2 minus sine of 0. And we know our trig values. This one goes to 0, this one goes to 1. And so we end up with 2 over 3 pi. And just with 1 second to spare. All right. So folks, definitely watch this video again. Come back to class on Wednesday if you'd like some extra practice. I am more than happy to work with you through problems. I may ask for your contributions, like tell me what you think your u is, tell me what you think your du is. It will not just be a show of me doing integrals, okay? But if you want some extra support, I am more than happy to answer those questions, all right?